Yeah, Andy Maiden. I'm from the University of Sheffield in the UK. I share my time at the moment between teaching in the university and research at the Diamond Light Source, the synchrotron there. There's been quite a few talks about ptychography. This one is sort of my take on some of the algorithms that you use for ptychography that enable the imaging that we saw in the last talk. I should thank these guys down the bottom here. These are my current PhD students. Ziyang is in the audience. Yeah, he's on that he's one of the core members. Wenjie there is helped with all this algorithm stuff. Freddie's not a boy wonder. He's not 12. I took these pictures from the university, central system. So he started as an undergrad with us. So he's actually in his mid-20s now. He's got a beard, which makes him look older. So I don't think I need to tell you what ptychography is. It's a method where we scan around a sample and we collect a series of diffraction patterns. So I've contradicted myself there because I have told you what it is. Scan around the sample, collect lots of diffraction patterns, and use some algorithms to form an image of what the sample was that made those diffraction patterns. In our group, so there's a lot of EM this week, we do some electron ptychography. Some examples here, we're trying to do ptychography in the near field, so it's a different regime. We put our detector in the near field, so close to the sample, or we image a plane close to the sample. And these are some of our results in collaboration with a group in Jülich in Germany, the Ernst Ruska Center, Rafał Dunin-Bukowski and Penghan Liu there. So on the left is a magnetic sample, a permalloy sample, looking at the magnetic fields in that permalloy sample. In the middle is a biased needle, so you can see the electric fields in the phase forming around the needle. On the right, this is one of my favourite ptychographic reconstructions of recent years. This is my postdoc's daughter's fingernail, and we imaged it with visible light. So this is an adult fingernail was too thick for the multi-slice reconstruction, but a two-year-old's fingernail was optically thin enough that we could do tychotomography with multi-slice. So it's multi-slice tychotomography with 5 slices in this case. So we rotate the fingernail around and do lots of ptychography scans to get that one. This talk I want to talk about the algorithms, the thing under the hood that enables us to get these images, or at least my take on them. So there's a lot of these algorithms. These are just a selection of papers dating back to about 2008 when this stuff started to sort of come online. And they generally break into 2 camps. There are sort of batch algorithms, and I've listed a few there, ADMM, difference map, RA, I'll talk about these later, conjugate gradient. And they're really good because they're highly parallelizable. So we can split the image reconstruction between lots of different workers, and they can all do a little bit of it, and we can parallelize that. And when we've got huge amounts of data, that's really important. They can be perfect with perfect data. I'll show some examples of that later. Also a very nice property. And pretty tolerant to noise, generally. The sequential algorithms, EPI is sort of my one. There's some neural network-based versions that use ADAM and stochastic gradient and things like this, proximal algorithms. They're more memory efficient, and they converge very quickly, and they're robust to initial conditions. They don't share the properties of parallelism with the batch algorithms. So the sort of theme of this talk is to try and get all of these properties into one algorithm. Okay. So I'll start with an example of these set projection methods to solve Sudoku puzzles, which I hope you're familiar with. We'll look at CDI, John's original contributions there. we'll look at how we can frame ptychography as a set projection problem. We'll see how we can implement these algorithms, and we'll do a bit of a comparison between them. So, how do we write an algorithm to solve a Sudoku puzzle? There's a number of ways to do this. Back projection is one of them, and set projection is another one of them. Sudoku puzzles, do you all know about Sudoku? Everyone knows Sudoku, right? You have to get the digits 1 to 9 in the columns, 1 to 9 in the rows, 1 to 9 in each block, and then of course your solution also has to have these clue digits correct. So there's sort of 4 constraints on Sudoku. And we can think of this problem in terms of a space, and the space is all the possible Sudoku grids, right? And we could step through every single position in this space, which would fill this grid with a random array of digits, and we could check if it matches these constraints, right? That would take ages. What we can do instead is we can put constraints in this space. So here's one constraint, that the columns have the digits 1 to 9. Another constraint is that the rows have a digits from 1 to 9. So that's a subset of the space. The blocks have the digits 1 to 9, and the clue digits are correct. Okay? So there are regions of this space where these constraints are satisfied, but hopefully, if it's a good Sudoku puzzle at least, there's only one point where all 4 of them are satisfied, okay? And that's the solution to the puzzle. So we can imagine an algorithm where we start with a random position, so we fill this Sudoku grid full of random numbers, at least numbers between 1 and 9. And then we can think about projecting onto each of these constraints. Okay, I'll tell you about projections in a minute. So this projection meets the column constraint. And then we can take that Sudoku grid and we can feed it into and find the projection onto the row constraint. Okay? So we can solve these sub-problems one by one in sequence and project between these different sets in this search space. Clue digits are correct. And then we can iterate through that. Project, 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 and hopefully we arrive at the solution. Okay? So, the question is, what is a projection in this Sudoku space? Okay? So, one way that we can do this, or find this projection, is we can take our Sudoku grid and we can represent it as a 9 by 9 by 9 cube. Okay? So I had to draw a lot of cubes for this PowerPoint. And we can represent the digit 1 by a binary string with 1, 0, 0, 0, 0 as our entry, okay? And the digit 4, we colour in the 4th cube, so we put a 1 in that cube and zeros in the rest, okay? So here's an entry in one row of this Sudoku puzzle, represented by that matrix on the top of 1s and zeros, which looks like this, okay? So we can represent Sudoku as a cube. And once we have that cube, we can assign the numbers, the digits 1 to 9, we can project onto something that's a valid solution for that row. So it only contains 1, 1, 1, 2, 1, 3, 1, 4. Using this, it's an allocation problem essentially, and you perhaps are familiar with these sorts of allocation problems, where so one of these salesmen has to go to Dallas, one has to go to Chicago, one has to go to New York, and so on. Okay, and you have to find the lowest cost. Okay, so Fred goes to Dallas, Beth goes to Chicago, whatever it is. Okay, exactly the same problem, and we can do this. Match pairs is the MATLAB function and does this allocation. So we can represent our Sudoku as a cube with these binary strings, and then we can do an allocation problem to find the projections onto the rows and the columns and the blocks. So, taking my life into my hands here, doing a live demo. Okay, so we're in MATLAB, and we've got an easy Sudoku puzzle here. So here's a Sudoku puzzle, and I laboriously solved the puzzle. Okay, so I've got the solution. So I can colour in the digits in here in green if they're correct. Okay, because I know the solution. I managed to solve it. So this is my random start point full of the digits 1 to 9. Okay. The first step in the algorithm, I've taken the column projection here. So if you look down each column, I've done that salesman problem, and each column now has the digits 1 to 9. Okay. If you look at the top row, it's terrible because it's got 4 1s in there. I can see 4 1s, right? So now we've got a new Sudoku grid where the columns are correct, but everything else is scrambled. So we take that grid and we feed it into the next projection onto the row constraint. Now all the rows have got the digits 1 to 9. We've done that allocation problem again. But where's some bad ones? The first column now has 9 4 times. Okay, but now we've got a new Sudoku grid, and now we can do another projection onto one of the other constraints, which is this one, the block constraint. Now all the blocks are correct, but it's screwed up all of the columns and the rows, right? The clue projection, where we replace all of the digits in the grid with the ones that we know from the start point, that's a strong projection, so all of the green ones are correct now. The error down here says how many digits were wrong at the start of this iteration. Okay. So we iterate through. And we solve the Sudoku problem, okay? Yeah? How do we know it converges? I don't think we do. We're just trying this method and seeing if it works, okay? So the method I just told you, the projections, alternating projections, okay, where we project between all of the different sets, doesn't work, okay? This is a different algorithm, which will be revealed later on, okay? In the Times newspaper in the UK, we have something called super fiendish Sudoku puzzles. Okay, and I also managed to solve this one, the super fiendish puzzle. But I think it's really interesting. So the same method, right? It's not quite the method I just described, but it's the same secret method that I'll tell you later. Same method. But now, and I think this is quite interesting, even though this algorithm is completely alien in terms of how humans solve Sudoku puzzles, it doesn't have any bearing on that. It still takes a lot more iterations to reach us. So there's something fundamentally hard about difficult Sudokus. It's not just that they're hard for humans, right? Is the solution unique? It'd be a bad puzzle if it wasn't. So yeah. If there were no clue digits, there's lots of solutions. It's a magic square, right? But they design these things such that they're unique solutions. Okay, so that's projection methods and what they mean, right? We project onto different constraints in various ways and try and find a solution to a problem, which can be broken down into separate sub-problems. So I'll use this flea. This is Hooke's flea from his Micrographia book. So a 1665 Hooke with the first compound microscopes painstakingly drew all of these amazing pictures, and the flea was one of the famous ones, okay? I'll use this as an example throughout. So in terms of set projections for imaging, originally, this is what John worked on back in the late 90s. We have this object that we want to image, and what we do is we mask it off in some way so it has a finite support, okay? Then we shine a laser beam or a beam of X-rays at this sample, and we record a diffraction pattern that looks something like this, perhaps. And we rely on a model of what's going on, a physical model of what's going on in this experiment. And if this detector is in the far field, then it's just a Fourier transform relationship between the multiplication of those two things, A and O. That's what comes out from the sample, the exit wave. And the diffraction pattern is the modulus of the Fourier transform squared. That's our model. So, just like with the Sudoku, we can frame this as a set projection problem. We've got all the possible images that we might reconstruct. One might be a flea, one might be an ant, and everything in between, okay? Within that set of all possible images, pixel matrices, is a set that has zeros in everything outside the support, okay? We've drawn that as a convex set. We also have a set of all the images that when we feed them through that forward model, generate the right diffraction intensity, the one that we measured. Okay? That's a non-convex set, which makes the problem much more difficult. The reason it's more difficult in this case, if we do our projections and things, we can get stuck in those local minima down there. Okay? And we might, unlike the Sudoku puzzles, there might be several solutions which compete, okay, so that we get twin images essentially, because there's several solutions that match both constraints. So if we do a quick simulation with Hooke's flea, we mask it off, then its diffraction pattern looks like this. And if we do the alternating projections method, where we set everything outside the support to 0 and do the forwards model, etc., it looks like this, and it doesn't work very well. Okay. If we do the other method, and this is the same method that we use for the Sudoku puzzle, then we do get this nice image of the flea's hind legs. Okay. Field of view is a bit limited in these methods, which is one of the big things about ptychography, right? We're going to step this aperture around and get a larger field of view. So yeah, I can't remember how long that movie goes on. So that alternating projection method doesn't work very well for the imaging, but this method here, and this is the method John used essentially in his work on CDI with X-rays, does work well in this, for this problem. Okay, so Sudoku puzzles, coherent diffractive imaging, ptychography. So you can think of ptychography like a Sudoku puzzle in 10 to the 9 dimensions, more or less, okay? We've got our flea, and we shine a laser beam at it, or a beam of electrons or X-rays or whatever. We record these diffraction patterns for lots of positions, where each position overlaps with the previous one, okay? You know all this. And we step it out so we cover the whole flea, because we want to image the whole thing. And typically, perhaps from 100 up to tens of thousands of diffraction patterns, we, certainly with our optical bench work that we do with visible light, use up to about 1,000 diffraction patterns with 1,000 by 1,000 pixels in each diffraction pattern, which is where the 10 to the 9 thing comes. So 10 to the 9 pixel measurements in our data set. So, just like the other two examples, we can model this as a set projection problem. One of our constraints, and I'll talk about what the space is in a minute, but one of the constraints is that in position 1, in the beam position 1, we have to generate the correct, our forward model has to generate the correct intensity, the one that we measured. And we have another constraint, slightly difficult to see, but the same thing for the second position of the beam. We have a constraint that says when we feed that beam position and our object through the forward model of our system, we must generate the correct measured intensity pattern, and so on and so forth. I've drawn these as circles here because they're non-convex sets again. Okay, so it's a difficult problem. But if we can find an image that satisfies these constraints, that matches the measured data in every position, then we're at that intersection of all of the circles, okay, and we've found our solution. So the way we can put this into a set projection framework is to define a space, and it's a weighted Euclidean space that sits in a product there in complex plane, complex D, where D is that 10 to the 9, the number of pixels that we measure. Okay, so it's a huge space. So to simplify things and explain the algorithms that we use, we could try, and this is essentially what the EPI algorithm does, we could just try our alternating projection methods where we project onto each of these constraints one by one, right? Oops, and hopefully we reach a solution. There's lots of different alternative ways to do these projections, and that's what I want to talk about next. So we'll reduce what we're talking about to just 3 constraints, 3 circles, okay? And here's our 3 circles in a MATLAB GUI. And so we've got an XY space, and we want to find the intersection of those circles, okay, using these set projection methods. And I've started at the blue circle there, which is just an initial, it's not random, it's whatever I put in the start point boxes at the top there. And alternating projections is the one we've talked about, where we project onto the red set, and onto the green set, and onto the gold set, and then that becomes our new position, and then we project onto the green. We're taking a random order here, so it goes green, what's next? You went straight to yellow, which happened to be then up to red, and then we move up there, and so on. Okay, and if we zoom that on, okay, it manages to find the solution in this one. We can do what's called under-project or under-relaxation of these projections, okay? So I'll just do an example of this with this parameter beta, which I've set to 0.5 more or less. So that calculates the projection, but it only moves half the distance, okay? It moves beta of the distance towards that projection. And then from that gold point, it moves half or beta of the way to the red set, and then beta of the way to the green set, and that's our new point, and we can iterate through that. It's getting a bit stuck now, okay? We can also over-project or over-relax, and I'm going to go up to 2, okay? Beta equals to 2. And then we go in the projection, so into the green set, we go the projection distance, but we go twice as far, okay? That's called a reflection. So we're reflecting about that set. Then we go to the gold set and we find the projection, we travel twice as far, so another reflection. So that algorithm is alternating reflections, okay? Reflecting between the sets. And that one goes nuts, right? Okay, unstable. You've got to be very careful with the step sizes and things in this, okay? I'll put beta back to 1. So now I want to tell you about the algorithms that we use for the Sudoku puzzle, okay? We start with average projections. That's what it says. So we find the 3 projections from our current point, and then we average, I'll reset that. And then we average them. So the sort of grey box there shows the averaging operation. So there's 3 points. It's the centre of mass of that triangle, right? And that's our new point. And we iterate that, find all of the projections. Can you see how this is parallel now? Each of those projections could be done independently and then brought back together. So not much point when there's 3 circles, but when there's 10 to the 9 of them, it gets more important. So that method gets stuck, okay? And if I sort of show the error landscape for this problem, I don't know if you can see that okay, there's some contours, but there's a local minima there, like the one we saw earlier, where this algorithm gets stuck. Sorry, the lights are a bit, make it difficult to see. So, let's do something a bit more complicated, but this, Douglas-Rashford, is the method we use for the Sudoku puzzle and for the CDI example, okay? So you have to pay attention for this one because it's a bit more complicated. The first thing we do is reflect around each set. Okay, you know what reflections are now. And then we find the average, hang on, I'll go back. Find the average, so average reflections now, right? Now what we do, we're going to take the green and the gold and the red points and we're going to reflect around the average point, right? So that's that. So the red point went from the top and it's reflected around the center point there, the center of mass down to the bottom there. Same with the gold and the green. And then there's another step. So we've got those 3 points now, the green, the gold and the red. And we've got the blue point, we're going to keep track of that one. And then we draw a line back to our start point and we travel halfway along those lines, okay? I'll show you it again. And we keep track of the blue points, okay? So we reflect, so this is the green reflection, this is the red reflection, and this is the gold reflection. And then we find the average of those reflections, and then we reflect again around those, and that gives us these points, the red, the gold, and the green. Then we draw a line back to our green point, our start points, okay? And then we're going to move halfway between the start point and the gold point, okay? Which is that. Now, we need to keep track of the red and the gold and the green traces for this algorithm to work, okay? That's the memory inefficiency, or that's why it requires more memory for these batch methods like RA and DM and so on that we use for ptychography. These represent exit waves essentially in the ptychography problem that we have to store. So if we keep iterating through that, then this is what happens. So that average point centers in onto the solution, but the gold and red and the green points, they spiral their way into points such that their average is the solution, okay? So they don't converge to the solution, okay? Those 3 tracks end up, so their average is the solution. And that's one of the big problems when you try and apply this to ptychography. Okay. So what we can do to help fix this problem is to relax some of these projection operators. So this is RA, relaxed average alternating reflections. And I'm going to set, I don't know what to set the parameter to, I'll set it to 0.8, okay? So it begins in exactly the same way as the Douglas-Rashford that we saw previously. We find the reflections around each set. We average those reflections. Then we reflect around those points. Oops, I've said it wrong. Hang on. I need to set it to 1.8, that's right. So reflect, find the average, and then we go, so this is a beta, a step of 1.8. 2 would be a reflection. 1.8 means I've gone to the projection and then 0.8 of the distance further along. So it's a slight relaxation of the previous example, okay? When I said it wrong, 0.8, it didn't quite go all the way to the center point. And that gives us these 4 points, and then we project those back to the start point, and we go halfway between the start point and that constellation of coloured points. And we repeat that again and again. Okay. And now we get really nice behaviour with all of the traces converging on the centre point, okay, because of that relaxation. So that convergence to the solution is, well, why Ra works better than DM or Douglas-Rashford when you do ptychography. Okay. I want to introduce some different methods now. I should just mention solvent flip. Because in Christoph Koch's talk on Monday, he mentioned charge flipping in the work he's doing on electron holography. And so solvent flipping is another name for that. Solvent flipping can be represented as projection onto the 3 sets, find the average, and then reflect around that point, and then go all the way to those reflection points. So it's projection, reflection, go all the way. Okay. The Douglas-Rashford was reflection, reflection, go half the way.
Recording in progress.
Great. Okay. And this one nearly gets there. And I guess that's why it's called flipping, because it's got stuck in some flip. Okay. Okay, so a couple of new methods. So I've got references for these at the end. I'll put a slide up with the references. I'm calling this one at the moment, I'm calling it relaxed average successive projections. Okay. So this one, we do our successive projections. So we project one by one onto the sets. So it's a serial, sequential method. But then we have another step where we average those 3 projection points. Okay. So we do the projections, then we average those points, and that becomes our new solution. Project, average the 3 projections, and that's our new solution. And that one gets to the solution reasonably well. We can also over and under relax this method, so I'll put this up, I don't know, 0.3. So we go slightly beyond the projection, slightly beyond the green projection, slightly beyond the red projection, but when we do the average, we still average the 3 projection points, the points where the lines cross their circles, okay? This one works really well for ptychography. I'll show you that later. And then off we go, and it reaches a solution. Okay. So bear that one in mind. That's the one I'll tell you about for ptychography in a bit. This, I think, is really cool. I'll put my beta back to 1. This is called string averaging. So forget the colours for now, because the colours represent something different. They represent a string of projections. So that string of projections went from red to green to gold. This string of projections goes from green to red to, from gold to red to green. And this string of projections goes green, gold, red, okay? So these strings we can compute separately, right, independently, okay? They do their own little sequence of projections, and those can be done independently. And then we combine together the strings by averaging their endpoints, okay? So each string results in an endpoint, and we can average those endpoints to get our new solution. And that converges nicely in this example. So the nice thing about this is we're starting to see the combination of sequential projections with parallelism, okay? So these strings can be done in parallel. And we can go one step further. We can combine this idea of the RASP algorithm, which I showed you, with the strings. So we do the same thing. We get a sequence of projections, or strings of projections. Well, those two are the same, which is annoying. So a string of projections, 1, 2, 3. And now, instead of averaging the endpoints, we're going to average all of the points where the lines, all of the projections, we're going to average them all together, okay? Which is what this big grey box represents. So all of those projection operations are going to average them together. And that gives us a new point. Oh, it nearly got stuck, but it made it there, okay? So you're starting to see the idea here of splitting things up into strings of projections and combining them together with this averaging operation. Right, I better move on. So how do we implement this in terms of tychography? All of these algorithms work for tychography pretty well. Okay, how do we implement them? I'll sort of breeze through this because you know it all, I guess, but we have our flea and our probe beam, which I've called P, and the probe beam shifts by this vector D, okay, and there's n, it's in the nth shift position at the moment. And the exit wave, phi, that comes out of this is just the multiplication of those two things. And then we've got the Fourier transform, and what we measure is the intensity squared of the Fourier transform. So when we're doing our projections, we take our current estimate, that's the current point in the circles thing, our current estimate at the flea, multiply it by the probe, Fourier transform it to give an estimate of the wavefront that we measured on our detector. We replace that wavefront's modulus with the measurement, and we come back. That's, you know, standard for all these CDI and tychography methods. We're not quite done yet, because what we then have to do is undo the multiplication by the probe. Okay, so we have to divide by the probe, and I've shown it as conjugate P over P squared there. It's the easier way to think about it. And that's one of the projections onto one of the circles in the MATLAB example. Okay, so this projection is badly behaved because there's a division by P, and P outside of the red circle, P is low, okay? So we have to be careful with those divisions. And what we can do instead is we can do a relaxed projection, okay, in order to help us with this division by 0. And so we do a weight between our current version of the object and our new version of the object after all the projections, after the projection. And if we choose a weight W, which is this one, then we get, that's the ePi algorithm. So you can think of the ePi as being a relaxed alternating reflections, okay? So a lot of those set projection methods relied on this averaging operation. So to explain how we do that bit in tychography, I've got some more of Hook's images, Hook's drawings, because each of these projection operations that we carry out, you know, onto each circle in the GUI, in the user interface, they could produce this set of images, right? Each one produces a completely independent member of the space, the search space, and those could be, one could look like a flea, and one could look like a bed bug, and one could look like an ant, and one could look like a fly. Those are valid projections. And the weighted average operation, because we're in a weighted space now, we don't just add all these up and divide by 4, right? We don't do that average. We do a weighted average of these estimates, and the weighting depends on the probe intensity. Okay. So that, well, actually, if we replace our ONU with what we had previously, okay, this is what you see in the literature for that projection, that averaging operation. It's a weighted average, and the weighting. So what it means is, we take this little bit of the fly, and we take a lot of that bit, okay? We take this little bit of the bed bug, this one, and we take a lot of that bit, but we ignore, or more or less ignore, all of the rest, okay? Because the probe intensity for these positions out here is low, okay? So it's a weighted average, and the weight depends on the strength of the probe for each projection. So yeah, you can look at the literature and see more information about these projection operations. But the point is, we can project onto each circle, and we can do the averaging operation, okay? I'm running slightly low on time, so I'll skip through these. So this is how we do it in MATLAB. We go through, so this is alternating projections, this is EPI. We do one projection, which is this operation, and then we update the object. And then we loop through and we do the next projection. So that's our alternating projections between the different sets. The average projections, we've got two loops now. So we loop through and we project onto each of the circle constraints, or we do each projection onto the data constraints one by one, and we store all of the outputs of those projections, and then we combine them together in this weighted average operation, okay? So that sum that I showed in the previous slide, we do a little loop to get all the entries into that sum. Okay. I haven't mentioned, and I won't really mention, that we also do this to solve for the probe function P. Okay, so one of the big things about ptychography is you can get the probe as well. That's just a separate set of projections going on simultaneously with the object projections. So I will share these slides, and you can have a look in detail. I want to get through to comparing these different algorithms since we're slightly low on time. So yeah, this RASP idea, relaxed average successive projections, we don't have to store the object ways. We can just the exit ways. We can just calculate the numerator and the denominator in that projection sum within a single loop. Okay, so that one gets to be more memory efficient. So this idea of strings and string averaging, what we can do with those strings is we can split up in terms of ptychography, we can split up the data into different workers, okay? So worker 1 gets some of the diffraction patterns, worker 2 gets another set, worker 3 gets some, worker 4 gets some. And each worker contributes a set of positions to that averaging sum, okay? So worker 1 gives us this set of positions in our reconstruction. Worker 2 gives us this set, worker 3 gets us this set. So each of the workers goes through its little string of projections and fires in its output so that we can combine them through that weighted averaging operation in one step. So you get the strings through the workers, combine them together. And that's how we can get parallelism when we're also doing these strings. Okay, I've clearly overdone the number of slides here, but let's get on to a quick comparison of how these algorithms work, okay? I think I've got about 5 minutes. So this is with noisy data. Sorry, the title is covered there. The EPI algorithm, that's the alternating projections. So it goes one by one through the projection. So after one iteration, it's already got a reasonable picture of the flea, okay? And then we're iterating. You can see the noise, okay? You can see the noise flashing about there. That's one of the problems you get with EPI is quite strong noise. Although it's converged, you still get quite a lot of noise. the Ra algorithm, which was that where we did the two reflections and then we relaxed it slightly and all the points converged together. That one deals with the noise much better, but I don't know why in this example, because it often works very well, but it's got rid of the high frequencies. So dealing with the noise, it's got rid of the high frequencies. This RASP idea, where we do the sequential projections and then average the projection points, does pretty well with the noise. So that worked very well in this example. With the strings, so the string averaging operation, after 4 iterations, that RASP algorithm is doing pretty well. And this one, because the strings are only contributing a small number of positions each, okay, it's slower in terms of convergence speed. But then after 100 iterations, they're more or less identical. Okay. So we get the advantage of parallelism with the strings, but we get a slowdown in terms of convergence per iteration. So this is a more realistic example where we're also solving for the probe in this example. So it's some blood cells imaged. It's one of our optical bench images from our ptychography scans. And this is the plots that came out. So this is iterations along the bottom against real space error. And this is perfect data. It's double precision, perfect data with no noise added. So the error is down incredibly small, times 10 to the minus 25. That's basically the working precision of the computer is the error here. So that RASP method, incredibly quick to converge. These relaxed versions of the reflection methods, they also converge down to the perfect solution. EPI, Douglas Rashford, and the average of projections, those other methods, they don't get anywhere near the perfect solution. Okay, and you can see EPI wobbling about a lot there, which is one of its characteristics. But to put it in a bit of context, 10 to the minus 5, 10 to the minus 4 in this particular error measure, you can't see the difference at all between the reconstructions. Okay. So it looks very impressive that you get down to these low errors, but the reality with real data is you never get anywhere near that. If we look at the string method, where we split up the projections between different workers, 2 workers is not twice as slow as a single worker, okay? So we're getting some benefit here in terms of speed, because 2 workers is about twice as fast because we can parallelize it, okay? 4 workers is not 4 times as slow, okay, it's about 3 times as slow, but we can do, the 4 workers can be independent, okay? So we're getting a gain here. Once we go to higher number of workers, we start to lose out to Ra, and Ra can be fully parallelized. Okay, so there's a limit where this splitting into different workers starts to diminishing returns. A quick movie, just to show how this relates to the circles and the projections in the circles. These are the 1 pixel in the reconstructions as we iterate through them. See the RASP one converging very quickly there. EPI's going nuts, just like that alternating projections one did in the circle. And you can see the Douglas Rashford one, which was the one that spiraled but didn't make to the solution, does exactly the same when you do it with ptychography. They have very much the same properties as the circle projections that we saw in the user interface. I'll flick through the noisy data, apart from to say that with very noisy data, which is this one, so up to only a maximum of 45 counts in the diffraction pattern here, very noisy data. What we've found quite consistently is just average of projections, so do all of the projections and average them through that weighted average, works really very well for high noise data. Okay, much better than the relaxed, more exotic methods that I showed, and better than this RASP average successive projection method. So yeah, final slide. So this is, in our optics lab, we didn't have a flea, but we did have an ant. So this is Hook's ant. And so we did a ptychography scan of an ant. And with EPI, we get this reconstruction. You see, quite noisy. With the Douglas-Rashford method, which is also DM, difference map, that Thibault originally described for ptychography, we get this solution, this image. Ra worked really well for this one. Okay, that relaxed version of the Douglas-Rashford gave a really nice, clear image of the ant. And this RASP method also is not a huge amount. I do think the RASP one is slightly better. Slightly more high resolution detail, I think, in the RASP reconstruction. Okay, so yeah, sorry I've gone on slightly longer than intended there, but I'll leave up the references for these different methods and yeah, ask you for any questions.